Okay, so our next speaker is Steve Flammia from University of Sydney. He will tell us something about the sparse quantum codes from quantum circuits.
Okay. Is this on? No. Hold on. Yeah, thanks to the organizers for having me here. It's been a great workshop so far, and I'm looking forward to the rest of it. So this is some joint work that I did with Dave Bacon, Aram Harrow, and Jonathan Shih, who's a graduate student at Cornell now. We all know what error-correcting codes are, what they're good for, but let me just briefly review some formalism for quantum error-correcting codes. So the most common quantum error-correcting codes, the ones that all of you here are probably familiar with, are stabilizer codes. So stabilizer codes are formed by mutually commuting Pauli operators that form a group that don't contain -1 in the group. And so just a really simple example of such a code that detects any single qubit Pauli error is a 4-qubit code. So here I have 4 qubits. And if I take the following tensor products, x tensor x tensor x tensor x, or z, 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 these two operators both commute with each other because the z's and the x's overlap an even number of times. And I can distill from this, I can distill 2 distinct Pauli algebras that commute with these operators but are not generated by them. So these operators are going to stabilize this code space pointwise, and I can look for operators that also fix the code space but only setwise, not pointwise. These are the logical operators. So I have here 2 Pauli algebras. So these guys each have the commutation relations of x and z. So if I have xx on top and zz on the left, they overlap in one place, so they anti-commute. By symmetry, I can just rotate this diagram and I'll get another one. And notice that this pair of operators here, so this guy obviously commutes with this, but this one also commutes with this because they overlap an even number of times. This one commutes with this because they overlap an even number of times. So here I have 2 commuting Pauli algebras, and I can store 2 quantum bits of information in these logical operators here. Okay, so just that's a quick refresher on stabilizer codes. Something you may be less familiar with is a generalization of the theory of stabilizer codes called subsystem codes. And the codes that I'm going to be talking about today are going to be subsystem codes. So this is an important slide. So the basic idea is to try to use excess logical qubits as a sort of gauge that we can throw away, that we're going to ignore. Okay, it's like a workspace. And the motivation for doing this is that I can make certain aspects of my code sparser if I take advantage of this extra gauge freedom that I'm going to introduce. Okay? So I can turn the code on the previous page into a subsystem code or a gauge code in the following way. So here are my 4 qubits. If I go back, I have these stabilizer operators. These fix the code space pointwise. Now what I can do is I can take one of those logical operators, I guess this one, and I can sacrifice it, okay? And I can turn it into a gauge operator. So I got a little mixed up, but you get the idea. One of these guys was formerly a logical operator. And this other pair of operators here, where did they come from? These guys are the image of this guy under the action of the stabilizers on the previous page. Okay? So what did I actually do here? There's a couple ways to think about this construction. One way I could think about these operators is these are 2 things. So first of all, these operators no longer mutually commute, right? So for example, this thing anti-commutes with this guy and with this other guy. So this isn't an independent set of logical operators that I've just defined right here. On the other hand, there are products of them, namely these products right here, GX1 and GX2, that give me back my stabilizers. So therefore, because this is the same operator that I had previously, these operators are going to commute with this pair of logical operators. So this operator will still fix some code space, and these things will commute. So I can measure this, and I can measure that, and I'll never disturb the state of this. But the point is that these gauge operators also commute with these logical operators, right? So that's less obvious, but we can check that. This ZZ here, for example, commutes with this pair of logical operators. So even though none of these operators here generally commute, some subsets of them commute, but these operators don't commute in general, I can measure each one of them. Then I can take the classical correlations between those measurements, right? So let's say I measure this guy and I get -1, and I also measure this guy and I get -1. I can classically just multiply the results of those measurements, and it's equivalent, as far as this logical qubit is concerned, to checking this stabilizer and saying there's no error on that stabilizer. Okay, is that clear? So yeah, it's a little bit slippery, I think, but the basic idea is I can split the stabilizer group into products of gauge operators. Those gauge operators don't have to commute. Measuring them messes up other gauge operators because they don't commute with each other. But the logical operators are still preserved. They will still commute with these. And the stabilizers, which are formed by products of these, also commute. So I learn syndrome bits by multiplying these guys together, and then I can decode and read out logical bits. Okay, so that's how subsystem codes work. Any questions? Yeah?
Is the composition also unique?
No, it's not unique.
Okay.
So the question was, is this decomposition unique? The answer is no. But we're going to see for the codes that I'm interested in, I'm going to define, there's a very natural preferred decomposition that we're going to use. But in general, this thing generates a group, and you could pick any generating set for that group. The generators are never canonical. Other questions? Okay, so yeah, so I sort of already went over part of this slide, but maybe it bears repeating. You know, I can talk about these codes abstractly in a very general setting. I can talk about defining my code by simply writing out a set of gauge generators. So I can just write down a bunch of operators that may or may not commute, and I can call them my gauge generators, and I can see what are the properties of the resulting code. And the way I would do that is first I would find the objects that commute with all the gauge generators, and these are going to be the stabilizers. So this is the piece that if I measure all of those gauge operators, this core bit right here, the center of that group, is going to commute with all of those measurements. So this information is preserved when I make those measurements. So this is how I'm going to extract syndrome. Okay, so those would be the stabilizers. And then the logical operators are again going to be logical operators are always, so in the stabilizer code case, they're always the things that preserve the code space set-wise, not point-wise. So here it's the same idea. They're going to commute with G, and they're going to permute the code space. So it's going to be the normalizer in this case. And there's a slight departure from stabilizer codes in that there's sort of two types of logical operators. I'm just mentioning this to be complete. I don't think I really go into this in this talk. But there's sort of two types of logical operators. There's bare logical operators, which have no component. So let me just skip that. It's a detail that we really don't need. Okay. So let me talk about sparse codes for a minute, why they're important. So first let me define some terminology, which most of you are familiar with. So if we have a code family on n physical qubits, that encodes k logical qubits and has distance d, then we use this notation, nkd. So you know, there's lots of properties that you care about for a code, and n, k, and d are just sort of some summary statistics that tell us some interesting things about the code. So we have an nkd code. This code encodes k logical qubits, corrects any Pauli error, or detects any Pauli error of weight less than d. We're going to be specifically interested in sparse codes. So we're going to say that a code is S sparse if all of the gauge generators have weight less than or equal to S, and also every physical qubit is acted on by at most S gauge generators. Okay, so this means that it's sort of sparse in two specific senses. No qubit partakes in more than S measurements, and I never have to measure more than S qubits at a time. Okay, so I can extract these gauge things with low depth circuits. So for example, classical codes, this would correspond to row and column sparsity of a parity check matrix, these two notions of sparsity. And I won't bother with this adjective S, I'll just say it's sparse if S is a constant independent of N. So sparse codes are really important. Probably all of us are carrying sparse codes in our pockets or in our like wireless signals, for example. They use what are called low density parity check codes and variants of these things. These were discovered in the 60s by Gallagher. There was some follow-up work on decoders for them in the 90s. There's a huge amount of work in the classical literature on using sparse codes because they're very efficient. That's the bottom line. They have really good distance, even at constant rate. They're very flexible. They're easy to decode. We would love to be able to emulate the success story in the quantum case. That's sort of largely open. I mean, people are making progress, but there's been a huge amount of work on sparse codes in sort of more than one setting. There's a kind of topological setting, which you might as well credit to Kitaev as being the pioneer, although I think a lot of people thought about these things over the years. People have shown that sparse codes can have very high thresholds. People have shown that the overhead for fault-tolerant computation can be very low if you have sparse codes, subject to some other conditions. So there's lots of examples of these things, and they roughly break down into two classes. Ones that have this topological structure, that is to say, there's a sort of metric, there's a topological space, and there's a metric on it. And all of these check operators, or these gauge generators, or in the case of a stabilizer code, the stabilizer operators, they're all geometrically local. And then there's the case where I don't worry at all about any notion of locality. And I'll just call those non-local, just to contrast them with this idea of the local codes, okay? Like I said, the major challenge, we want to be able to produce sparse quantum codes where K and D are both proportional to N, that's the best you can do, and where we have fast, nearly optimal decoders. Okay, that's the outstanding challenge. If any of you solves that during my talk, that's great. You should publish that. Let me tell you a little bit, before I get to our contribution, let me tell you a little bit about the prior work. So what was known about, so first of all, what's known about general codes? I mean, I said, so this is a plot of K and D, and I'm going to put some points down where we know that we have achievable pairs for K and D. And so first of all, if I don't care at all about sparsity, if I just have a dense code where I have to measure order n qubits to extract one bit of syndrome, it's been known since the 90s that I can have a good code, a so-called good code, where both K and D are proportional to N. It took almost 20 years for people to be able to improve on that. Bravi and Hastings showed last year that you can keep these parameters, D and K scaling proportional to N, if the weight is only root N. So they made an improvement there. But we want sparse codes where the sparsity is order 1, so that's not good enough. So let's look at what's known about sparse codes, what was known before our paper. So there were a bunch of papers known. These papers, some of these are local codes, some of these are non-local codes. So Kitaev and the Toric code, Friedman, Meyer, and Luo improved on that a little bit. These are codes that only encode a constant number of logical qubits, but the distance scales like root n. Friedman, Meyer, and Luo improved that a little bit with this square root log n factor. Some other examples with non-local codes were derived by Tillich and Seymour, and also Bravi with a subsystem code, and Guth and Lubatsky, they have codes with these sort of parameters here. These are all very nice code constructions. So our first new result is the following point here. This is an achievable point in this diagram. So we have a family of non-local codes, subsystem codes, that achieves the following. We can encode a constant number of qubits, and our distance is 1 minus epsilon. where epsilon, anytime you see an epsilon in this talk, epsilon is always 1 divided by the square root of log n. But I'm going to get sick of saying that, so epsilon is slightly smaller than an arbitrarily small constant. It actually decreases with n. So this is our first result. If I restrict to local codes, so now these are sort of a very natural class of codes. We have experimentalists interested in building surface codes and things like this. So what's the story if I restrict myself to surface codes? It turns out that there are some extra constraints in this diagram now. You can't just have anything you want. If you have a capital D dimensional space, then there are some restrictions. So Bravi and Terhal showed that the distance can't be too large. It can scale at most like n to the power 1 minus 1 over d. And moreover, there's a trade-off between the rate and the distance. And you have some other inequality, which I've tried to sketch out. Bravi, Poulan, and Terhal proved that. And so our next main contribution, so now I've sort of grayed out these non-local codes. This line here is the special case d equals 2. So in d dimensions, we come up with codes that saturate this other bound by Bravi, Poulan, and Terhal, and almost saturate this Bravi-Terhal bound up to this, again, this epsilon factor 1 on square root of log n. So we get very, very close to the edge of the achievable region for local codes as well. We don't know how to boost our rate up. That's going to be one of our open problems. But these are, if you care about parameters and not constructions, then this is sort of our main results. So how do we do it? The way we do it is everything is built through the following main result. We take a stabilizer code, which has the following parameters, n naught, k naught, d naught, and a fault-tolerant circuit that can measure the syndrome of this stabilizer code. So fault-tolerant circuit, it extracts the syndrome, and that circuit has some bound on its size given by S. Then we have a procedure, constructive procedure, which builds a new code that sparsifies everything. And it preserves these code properties. But the problem is, the K and D code properties, I mean. But we incur a little bit of overhead. Right? So we preserve these K and D parameters. But the price that we pay is that the number of qubits that we, the number of physical qubits that we gain is proportional to this circuit size, plus the size of the original code that we started with. Okay? So all of our other results, our specific parameter improvements are, can somebody hand him the mic? Our specific parameter improvements are all corollaries of this main result.
How sparse is it?
13 sparse?
Something, yeah. I'll look it up.
Yeah, I think it's 13 or 14 sparse. We had some ideas to make it 3 sparse. I haven't worked those out with sufficient care to have any confidence in saying that it's 3 sparse. But we don't feel like there's any obstacle to getting it down as low as 3. I think it's fair to say, but it might take some hard work. So let's go with 14. I know 14 is an upper bound. Yeah, so I'm not going to get into that many proof details, but I'm going to go over the construction and give you the intuition. The construction itself is really simple and elegant. I really like it. So like I said, we begin with a stabilizer code of your choice. This is the simplest stabilizer code. This is a classical code, but it's going to illustrate some of the ideas involved. And now what we want to do is we want to write a Clifford quantum circuit to measure the stabilizers of this code. So here's such a circuit. So you'll remember on the previous slide I said it has to be fault tolerant. Let's not worry about the fault tolerance for the moment. I'm going to sort of glue that on at the end. So here's a circuit for measuring the syndrome. All this does is just copy the bits of these two. It gives me the parity, and then I just check. So just a word about notation. So in my diagrams, time is moving from right to left. So I can think of this object as just being a linear operator, and I can read it off from the circuit by going that way. And so this thing then acts on this state. This thing here, then I can think of that as like a partial trace or a post-selection on this state, or on this circuit, okay? So time goes that way, data input, ancilla preparation, post-selected measurement. Just said all those things. So the mapping proceeds as follows. We're going to turn time into space. So everywhere there's a step in this circuit, I'm going to add a new qubit, and that's going to be a new physical qubit in the new code. Okay, so this is why it scales like the circuit size, because we have to transform the circuit in exactly this way. That's why we pick up this circuit size. And now I'm going to define a gauge group associated to this. So the gauge generators are going to be added via what I call polycircuit identities. So let me just zoom in on this C0 gate right here, and let me define what I mean by polycircuit identities. So if I put in an X tensor I operator on the left, and I propagate it in time to the other side, then this C0 gate is going to copy that X error down to the second wire, and I'm going to get 2 copies of X. So this fourfold product on these 4 qubits is a polycircuit identity. Because the combination, if I multiply this C0 gate on the left by XX and on the right by XI, it stabilizes the C0 gate. I get a C0 gate back again. Okay? Similarly, I can do the same thing for a spanning set of poly operators. I can do it for IX, that propagates in this way. And I can do it for ZI, that propagates this way. And I can do it for IZ, that propagates this way. So all of these things stabilize this C0 in a similar way to stabilizer operators in a stabilizer code, stabilize code words. Yet another way you can think about this, if I do like what, for example, Debbie had in her diagrams, if I look at this choice state, if I just bend these wires around, then the operator Z, Z, I, Z stabilizes the choice state of this unitary, right? So there's several ways you can think about these operators. So for every single circuit element, I'm going to find what its local Pauli stabilizers are, what the Pauli circuit identities are for that circuit element, and I'm going to throw it into this gauge group. And I'm going to do that for every circuit element. And so here's a dictionary. For every element of a Clifford circuit, now remember, since I'm interested in stabilizer codes to start with, all of my syndrome measurement circuitry only consists of Clifford operators. I mean, I suppose you could put in something more than that, but we restrict that our circuits are always Clifford. So here's a set of generators for Clifford circuits. The identity gate, these are the gauge generators, and so on. So you just look it up in this dictionary. That's everything you need to know. And this implicitly defines the code, right? So the gauge generators generate the entire code. But now we need to analyze it, right? This is a very implicit definition of this code. What we would really like is an understanding of what do the stabilizers look like, what do the logical operators look like, and what are these code parameters. So how do we do that? In order to do that, we have to understand a little bit about how this code space gets preserved when I add these extra, when I enforce each of these Pauli circuit identities as I go through this circuit. So first of all, if I look at this circuit as a linear operator in the way that I was saying before, I can think of this operator. It turns out this operator is just the following projector. It's just the projector onto the code space. So we say that that a circuit is good, it's a good circuit, if this linear operator, if V dagger V, call this V, if V dagger V is equal to the code space projector. One property that we need is this idea of gauge equivalence of errors in here. So suppose I have an error, and it's here at time step 2, and let's just call that error E. So let's say I put an X error on this qubit. I can apply gauge operators to this, and I can move this error around. So for example, oops, if I have an X here, and I apply the gauge generators associated to this C0 gate, that would consist of an X, an I, an X, and an X. I can cancel this X at the cost of propagating the error over to these 2 sites here. Right? So I just applied that gauge identity to this code, to this error, sorry. And I can do that again I can apply it again on a different identity to map it over here. And if I do that, I can always push errors around on the circuit and it's never going to change. So if I look at the linear operator associated to the circuit plus some pattern of errors, it's always equal to some gauge equivalent version of that with the action of the gauge group up to some overall sign. And so we can get from this something we call the squeegee lemma. It's basically a cleaning lemma, those of you who know something about subsystem codes. We can pull our gauge operations until we localize all of the errors onto the initial data qubits. So we just keep applying gauge generators until all of our errors are mapped to the boundary. The boundary is where our initial code sits, right? That's where we would feed in code words in order to measure syndrome, right? So it's kind of natural to push all of the errors onto that boundary. So there's another operation called spackling, which is like squeegeeing, but you leave a residue. So yeah, spackling, for those of you who don't know, is, I got this wrong when I talked about this in Zurich. I confused it with grout. Spackling is like if you have a hole in your wall and you have to cover it up and you sort of leave a residue. Anyway, spackling lemma sounds better than the grout lemma. So okay, so what is spackling? Spackling is I look at the world line history of an error or of a set of operators that start at the right-hand boundary. Okay, so I'm going to define an operator sitting on the boundary of this circuit. So that would be an operator that's naturally associated with the original code that we started with. And then I'm going to follow its time history as it goes through this circuit. So if I were to propagate this forward in time through the circuit without any errors, then here's what would happen. This X error would copy down and go to this register. This one would just go through. This one would go through. And then this one would copy down. This one would go through, but then they would cancel. Right? So then this tensor product of these 7 X operators is the world line history. It's like the world sheet, I guess, of these 2 X operators right here. So it turns out that the spackle of the input logical operators generates the logical operators of the new code. So for example, this XX is a logical operator for this 2-bit error detecting code. It's the code that flips 00 to 11 and vice versa. Similarly, another logical operator is just Z on one of the qubits. These 2 operators anti-commute. Their world sheets define the new logical operators of the new code. Yeah. Similarly, we can spackle stabilizers of the old code, and we get the new stabilizers. So ZZ was a stabilizer of the original code, and if I spackle it across and I look at its world sheet, then I get one of the new stabilizers. And I can do that for all of the original stabilizers. I can also do it for these ancillas. I think of this ancilla as sort of being a 1-qubit code. It's a 1-1 code, and it's stabilized by a single operator Z, right? So I can spackle those through as well. So here's a syndrome, or here's the stabilizer for that ancilla operator right there, ancilla state. So this characterizes the stabilizer operators and the logical operators for this code. Everything else is either a gauge operator or a detectable error. So this completely classifies our code. In terms of the algebraic properties, at least, I haven't yet said how to get the distance. These 2 ideas of spackling and squeegee, they basically imply an isomorphism between the code spaces. K is preserved under this transformation. To control the distance, we need another property. So for syndrome measurement circuits, general ones, this new code is uninteresting because distance isn't preserved, and anybody who's ever cleaned their windshield that has a bunch of, after driving on the highway, you have a bunch of bug splats, and then you try to squeegee that, the bugs get delocalized everywhere on the boundary of your windshield, right? So the point is this, that if I have local errors in the bulk, if I have local errors sitting in the bulk, and I have fewer than D of them, right, then these are detectable errors. But when I squeegee them, if they propagate and they spread all over the place, they might not squeegee to a correctable error on the boundary or to a detectable error on the boundary. So I need some way to control the spread of errors. Well, what do we know that controls the spread of errors? Fault tolerance controls the spread of errors. So we need that our circuit is fault tolerant if we want to try to preserve the distance. So it turns out this is true. We want to define a notion of fault tolerance for our circuits. We have some sort of strange constraints relative to normal fault tolerant theory. So the entire circuit has to be Clifford. So for example, we can't do a majority vote. That's sort of a classic way to achieve fault tolerance, is you repeat things a couple times and you take majority votes. Because everything has to live in this circuit, we can't do that. We're not allowed to do classical feedback or post-processing for the same reasons. On the other hand, we have a sort of unique advantage in that we only care about detecting errors. We don't care about correcting errors. So the fault-tolerant gadgets, I'm running a bit short on time, so I'll go quickly through this. But the basic idea is to build on a sort of Shor DiVincenzo cat state type approach. So here is a bunch of data, and then we're going to use a cat state, right? And we're going to couple the cat state to the data to try to get parity information out. So here I've drawn a circuit that just measures, I guess, X stabilizers. So it measures X, tensor X up here on the data block. And you can imagine there's a bunch of other wires that this gadget doesn't touch. So for every syndrome, I'm going to embed it with one of these fault-tolerant guys. And what we do is we enforce, so this cat state here propagates things. It's like if I have an error right here, it will propagate when I push it this way. And these, what I do is I define a parity block down here, which couples, it couples pairs of terms back up here in the cat block. And it does this in a way that the entire thing can be fault tolerant. If I choose that the relationship for how these things are connected to each other is a constant degree expander, then this circuit can have size order W if I'm measuring a weight W stabilizer. Okay? So we have these fault tolerant gadgets. They work. We have a sort of uniform construction for these things. Constant degree expanders are sort of known to exist, so we can just appeal to known results to show that we can always find such a thing. And we can choose the degree of the expander to be like 7, which is how I got the number 14. So expansion is actually a little bit stronger of a property than what we need. We need a slightly weaker property called well-linkedness, which just guarantees that a sort of subgraph of this thing is expanding, just expanding on a subset. So the definition of it expanding would be optimizing over all subsets. We only have to optimize over certain subsets in order to get the property that we want. So this can probably be improved, but we haven't thought enough about it. Okay, so let me just recap all that. So the main results, stated a little bit more precisely, you start out with an N0, K0, D0 quantum stabilizer code with a bunch of generators, weight W1 through W N minus K, N0 minus K0. Then we have a circuit that has about size sum over these weights. And I can find a new associated NKD quantum subsystem code where all the generators have weight order 1, and the K and D parameters are preserved, and the circuit didn't grow by more than the sum of the weights of the original generators. Okay, so that's the main result. And the recap of the proof technique, spackling shows that K is preserved. Squeegee lets us pull the errors back to the original code. Fault tolerance ensures that the weight doesn't grow. And then we have constructions that give us low weight stabilizer measurements that are also fault tolerant. Okay, so that's the result. So now some of these corollaries, how do we get some of those? So the first one is if we start with a random code that encodes 1 qubit, and then we concatenate it a bunch of times. So I concatenate this code m times with itself. If I do this, then the sum of the stabilizer weights is n0 to the power order m. And if I plug in a specific, if I optimize the choice of m to be root log n, then we get the first result that I claimed, right? That we have a NKD code where d is almost as large as n, off by this factor epsilon. So the previous best distance for sparse codes was this stabilizer code by Friedman, Meyer, and Luo in 2002, which only beat, it was only root n root log n. So the second result is because these things are circuits, I can imagine trying to spread this circuit out into a local geometry, right? So I have a grid in 2 or 3 or in general d dimensions, and I'm gonna run my circuitry for this code through the vertices of this grid to try to make everything local, okay? So what happens when I do that? So I can use things like swap gates and wires, identity gates basically, or wires. I can spread this circuit out. If the linear dimensions of this circuit are L, then this is the volume of the circuit, L to the D in D dimensions. Our next result is that you can take that concatenated construction and you can sort of spread it out onto the vertices of this lattice in such a way that you get the volume minus 1, so you get a surface scaling minus this epsilon. So this almost saturates this Bravi-Terhal bound. For local subsystem codes in D dimensions, yeah, this is this Bravi-Terhal bound that I was just saying. The best known local stabilizer codes, on the other hand, obey the following bound. So we can beat this in large enough dimensions. There's this other strange bound from this Bravi-Poulan and Terhal paper. For local commuting projector codes, we don't know that such a bound also holds, because the class of local commuting projector codes it's a distinct class. Like some subsystem codes are, like stabilizer codes are local commuting projector codes, but subsystem codes with non-trivial gauge are not in this class. So we don't know that such an upper bound holds, but we do know that for our class of codes, we do at least as well as this bound would suggest, and we might do better. So the way that we achieve this scaling is we use a construction by Talish and Zamor, and we plug it into our main result again. So then the last thing I want to say in the last few minutes is some speculations. When you talk about local codes, one of the most interesting outstanding problems is the idea of a self-correcting quantum memory. So what is this idea of self-correction? Many of you in the audience will be old enough that you remember what this is. This is a magnetic hard disk drive. Don't laugh, I'm teaching undergraduates StatMech, and they look at me funny when I tell them about magnetic hard disks, so we're all getting old. There's 2 states, all spins up and all spins down, and I can encode 1 bit of classical information into the ground state of the Ising ferromagnet, which is a toy model to describe the physics of this system. So what happens in the physics of this system is if I flip one of these spins, then I'm going to pick up an energy penalty proportional to the boundary, proportional to the number of neighbors of this spin. You can just see that from the Hamiltonian here. If I flip the neighbor of that guy, then this boundary is going to increase, so my energy penalty increases. And I can keep going. And if I take some kind of continuum limit, we see that I can flip a droplet of spins, and the energy penalty that I pay is proportional to the perimeter of that. So the energy penalty scales like the boundary of the region. So that means that this model has an energy barrier. In order to go from one state to another state, I have to flip, by the isoparametric inequality, I have to flip a bunch of the spins, and I can't do better than to have a circular droplet. So I'm going to flip order L spins. There's going to be a boundary of size order L at some point during the course of any Pauli walk that I take to try to flip these spins. Okay? So the Ising model is going to have this energy barrier behavior. So energy barriers are a subtle point. I don't want to get into, there's some experts in the audience who know that there's a very complicated relationship between the idea of self-correction and energy barriers. And I don't want to get into that very complicated relationship. I'm using this as a motivating idea. But basically, you can imagine, here's one code state, here's another code state. suppose I'm sitting in thermal equilibrium at KT and KT is small, right? Then it's intuitively plausible that it should be very hard for thermal fluctuations to kick me up and over this energy barrier and for me to move over to this other code state, right? On the other hand, if I had a very small energy barrier, if my energy barrier were order 1, then thermal fluctuations, I could just hop around here and eventually I would walk my way over to this other code state and my information would be destroyed, okay? We would like to be able to construct codes that have an energy barrier or have a sort of the self-correcting type behavior that's suggested by this cartoon picture with this energy barrier. One thing that's known, I should probably have a slide about this, one thing that's known is that in 4 dimensions, 4 spatial dimensions, the 4D analog of the toric code has this property. It has a large energy barrier. It has, you can't move from one ground state to another ground state, even at small finite temperatures. It's a stable quantum memory that sort of self-corrects. And it does this in part because the way the logical operators look like in the 4D toric code is they look like membranes, just like this. So they pick up an energy barrier. Whereas in the regular toric code, they look like strings, right? And so strings have no scaling. The boundaries of those is the only place that you pick up an energy penalty, so there's no energy barrier in the toric code. Okay, so what's known about subsystem codes without strings? So it's known that all 3D stabilizer codes have an energy barrier of order log L. So this is sort of widely seen as a, well, I don't know about no-go, but it's a not encouraging result for self-correcting stabilizer codes in 3D. So our subsystem code parameters, if you plug in d equals 3, we have a subsystem code that has L to the power 2 minus epsilon is the distance of this code. So it does not have any of these string-like logical operators that destroy the information in the toric code. So on the other hand, so it has no strings at all. So on the other hand, it's a subsystem code, so I can't immediately conclude that it has any kind of energy barrier. Subsystem codes with very large stabilizers are unstable. It's known that you can't have a self-correcting memory if all of your stabilizers all require multiplying n bits of gauge information just to extract 1 bit of syndrome. Because if any one of those things has any error on it at all, no constant error would be stable, right? Think about computing the parity, noisy parity, with constant error on each bit, and you have to do it parity of n bits. You can't do that, right? On the other hand, because of the way we built this with a concatenated code, a constant fraction of our stabilizers have constant weight, right? So we might be able to get around these sort of no-go ideas. So it's all kind of speculative. I see I'm running out of time. Yeah. So let me. This is some overview of a bunch of things that don't quite work as self-correcting memories in 3 dimensions. If we have, so yeah, a little bit more speculation then, just in the last couple minutes. So what I have in mind, I didn't say it very explicitly, but these codes, I can take minus the sum of the gauge generators, just like you take minus the sum of the stabilizers to build a Hamiltonian for the toric code. And if I do that, these terms don't commute. These Hamiltonians are going to be very hard to analyze in general. Sometimes these things are gapped, and sometimes they're not. So we don't even know if there's sort of this type of physics you associate with topological systems in these models. On the other hand, there's some hope that we have a pretty rich set of models here to study. The simplest possible example of our code is just a 1D wire. And this is exactly this Kitaev-Majorana wire, right? So in some sense, these codes are a very large generalization of this Kitaev wire, where instead of just wires, we allow arbitrary circuits. Now, we don't specifically talk about the physics of fermions necessarily, but it reduces to Kitaev's construction in the 1D limit. So, this is a class of systems that, it's enormous. It's going to have a very rich phase diagram. It's conceivable that there might be a gapped self-correcting phase somewhere or something very interesting in these systems. So to conclude and wrap up with some open questions, so I showed a generic way to turn stabilizer codes into sparse subsystem codes. I think some of the open questions are, what are the limits for sparse stabilizer codes? Can there be a self-correcting memory using the gauge Hamiltonian associated to one of these codes? The one that Aram and I have thought a little bit about is how to decode these codes. So I said for our concatenated codes, a constant fraction of our stabilizers have constant weight. So we might expect that there would be a threshold for such codes. Maybe there's a threshold. It's unclear. We've thought a little bit about decoding these codes. It would be nice if we could take some of these same parameters and also just improve the rate. And it would be nice if we could feed this construction back in on itself. If I didn't have to start with a stabilizer code, but I could start with a subsystem code as well. We don't know how to do that either. So there's some nice open questions here. I hope some of you will get inspired and think about it. Thank you.
Steve, you made this intriguing to me claim that this is a vast class and it expands over the Majorana-Kitaev wire. Yeah. Maybe I'm familiar with the latter more in the fermionic language and I didn't pick up enough of the analogies. Can you elaborate a little bit on that?
Well, yeah, sure. So the wire itself is just identity gate. The identity gate has the following stabilizer. If I put in an X, I get out an X. If I put in a Z, I get out a Z. Right? So now if I have a wire of identity gates, right, a perfect wire that transmits one bit of information, one quantum bit, then the gauge generators are just going to be XX, ZZ, and then I hop a site XX, ZZ, and so on. So I'm going to get the Lieb-Schultz-Mattis chain, right? I'm going to get a sum of XX and ZZ. And as long as I don't tune the couplings to be exactly equal, this chain has a gap, right? So I exactly recover this model.
And what about the generalizations?
Well, the generalization is just the way that you solve that model is sort of, you can apply these same ideas. So, okay, they solve everything about that model, right? Lieb-Schultz and Mattis, they get the spectrum, they get everything, right? So I don't expect that you could do all of that. But I think you could still extract some, I mean, we do extract the code properties. So we extract, for example, the logical operators, right? So for that chain, you construct the fermions with like a Jordan-Wigner type transformation. And if you pull those fermions across to the other side, right, then you get strings. I mean, it depends on the parity of the length of the chain. But you get strings of X's and strings of Z's. And when these anti-commute, you know that there's a degeneracy in the chain, and there's a twofold degenerate ground space, right? So we can do that same argument for an arbitrary Clifford circuit, and it would be the ground space of the associated gauge Hamiltonian. So that same argument is the thing that we've generalized, that we can characterize exactly ground space degeneracies and, in fact, code distances, if you treat them as codes, for any such Hamiltonian that you write that has that property. That's the sense in which it's a generalization. I mean, it doesn't have, it's not going to have, like the fermionic fields aren't going to necessarily all be localized and things like this. Like, it's not a, you would like to identify smaller classes that capture more of the physics to make it a better, a more useful generalization from the physics point of view. But in terms of, there's going to be something interesting if we can understand something about these Hamiltonians. I'll say that.
This major challenge that you mentioned at the beginning, sort of order n logical qubits and order n distance, I mean, can one at least try numerically and see if you have any hope of getting something like that? Because you're like at order 1, right, for the...
Well, for the rate.
No, this major challenge that you said if we can, solve while you're giving your talk, that one.
Did you solve it?
No.
Oh. No, so that challenge is are there codes, can you find n-qubit quantum codes where both k and d scale proportional to n?
Right, so can you check it sort of numerically at least? Is there any hope for that, or?
We build in by hand that our rate is, that we have one logical qubit. And we do this because we don't know how to prove the theorems if we let it grow. I mean, I think the construction still works for any k and any d, but we only get those new and interesting parameters. Yeah, and I don't think any numerical searches would help with that.
Yes, so about the Bravi-Polan-Tahar bound, so there are, I think, two versions of the bound, one for stabilizer and the other for subsystem. Which one are you talking about?
Probably the subsystem one.
I see.
Yeah.
So they have different exponents.
Yeah, I mean, I intended to show the subsystem one.
Okay, and the other question is, when we talk about subsystem code, even when it has large distance, sometimes it doesn't have any threshold, right?
Yeah, that's right. So
in the example with this very good code distance, does it have the threshold?
We don't know. So the reason let me talk about an example where we know that it doesn't have a threshold, and that's the Bacon-Shor code. So this is a subsystem generalization of Shor's code, and the stabilizers. So it lives on an L by L grid, and the stabilizers have weight order L. And in order to extract one bit of syndrome from this code, I have to multiply L bits of gauge information, right? And so if each one of those bits has a little bit of noise on it, and I have to add up L of them and take the parity of that, then unless my error rate is like order 1 over L, then I'm going to have a constant probability of error for every bit of syndrome that I read out. So there's no threshold in the Bacon-Shor code. The reason why some of our codes might have a threshold anyway is that if I use this concatenated code construction, then a constant fraction of our stabilizers all have constant weight. And so I can get those bits of syndrome. That may not be enough to label enough errors that I still have a threshold. That's an open question. But it's at least the same argument that kills the Bacon-Shor code doesn't kill this code. You need a stronger argument to kill this. And it might in fact work. I don't know how hopeful I am. I wouldn't want to wager a large sum of money or anything. But it's not obvious that this will fail. Let me say that.
One more question, so it's more speculative, but this construction has some flavor of holography, and do you see any connection?
It has some what, sorry?
Holography.
Oh, holography. Oh, no, I mean, I wish I could see a connection. Aram and I were calling these holographic codes at some point before your paper came out. Yeah, well, yeah. We don't know how to make a legitimate connection to ADS-CFT, for example. But yeah.
Okay, let's thank Steve again.